Hello, welcome to this lecture on advanced electric drives. In the last lecture, we have seen that in a vector control drive, the torque response is quite similar to that of a separately excited DC motor. The torque is proportional to the torque component of current, that is IQS. So, in this lecture, we will see the variation of the flux on the effect of vector control drive. But before that, let us try to see the response of the vector control drive under torque control. So, we will be discussing on the response of the vector control induction motor drive when we want to change the torque. Now, we have seen that the torque response of a normal induction motor is given by the following equation. Te is equal to 3 by 2 into P by 2 into Lm into IQS IDR minus IDS IQR. And we can also simplify this equation 3 by 2 into P by 2 into Lm by Lr IQS psi dr minus IDS psi qr. And this equation is a general equation which is also true for a drive or for a motor in a synchronously rotating reference frame. So, we can take this dq axis rotating synchronously with the rotor flux vector. So, we can have a superscript here. So, we can say this is also true for IQAC, psi dre, IDAC and psi qre. And in a vector control drive, we have seen that the dq axis are rotating with the rotor flux vector and the d axis is aligned with the rotor flux vector. So, we see that in a vector control drive, psi dr E is equal to psi r and psi qre is equal to 0, because the d axis of the reference frame is aligned along the rotor flux vector. If this is the d axis and this is the q axis, we can call this to be dE and QE. The d axis is aligned along the rotor flux vector. This is psi r, and hence we can say that psi r equal to psi dre and psi qre equal to 0, which is the condition for a vector control drive. Now, if we apply this particular condition to this equation, we can see that this part will vanish. This will be equal to 0 because psi qre equal to 0. So, if psi qre equal to 0, the torque equation becomes a very simple equation. So, we can say that the equation for the torque is equal to 3 by 2 into P by 2 into Lm by Lr. This is IQS E into psi dre, and which is quite similar to that of a DC machine. In the DC machine, we have seen Te is equal to K into Ia into If. The torque is proportional to the armature current and torque is also proportional to the field current. Here we are ignoring saturation. Similarly, if we can say that psi dre is constant, the torque equation is given by 3 by 2 into P by 2 into Lm square by Lr into IQAC into IDAC. This equation is quite similar to that of a DC machine equation, and we say that IQAC is called the torque component of current and IDSC is called the flux component of current, similar to the armature current of a DC machine and the field current of a DC machine respectively. So, this is the equation for a vector control drive, and we understand that in a vector control drive the torque can be controlled similar to that of a separately excited DC motor. In this case, of course, we have two options, either to vary IQS or to vary IDS, and normally IDS is comparable to the field current. So, we want to keep the flux constant at the rated value. So, we keep IDS constant, and what we do, keeping IDS constant, we change IQAC, we keep this constant. Usually what we do, we keep this constant and we change this one to control the torque, and if we change IQS to control the torque, torque will be controlled instantaneously. So, we can see that by a control block diagram. So, if we see that by a control block diagram, it will look like this. Say for example, I have two variables in this case. One is IQAC and I have IDAC, and I will multiply that by LM. What I will obtain here is psi dr, and here I have again a gain block. In this case, I can multiply by 3 by 2, P by 2, into Lm by Lr, and output is my Te, and this is my control block diagram. So, in this control block diagram, what I can do here is that I can keep IDAC constant. So, it means this component I will keep constant. I do not want to vary this, because if I vary this, the flux is going to vary, and if I vary the flux, the response will be sluggish, because any change of IDAC will not be accompanied by an instantaneous change in the flux. Flux will be delayed by some time, and that will be resulting into the delay in the torque. So, we can change IQS. If we see the response, I can plot this against time. All the variables I can plot against time. In this case, let me keep IDAC constant. So, this is my IDAC. And then what I will do here, I will change IQAC. IQAC was initially something here, and then here I will apply a step change. This is IQAC. Then what about the torque? The torque will vary proportionately. So, if I show the torque was initially like this, and as soon as I change the IQAC, torque will change proportionately. So, this is my torque response. So, it means if I want to have very good torque response, I would definitely keep IDAC constant and change the torque component of current. IQAC is called the torque component of current to have an instantaneous change in the torque. The torque can also be decreased. Torque can be increased. In the same way, torque can be decreased. Torque can also be made negative, because IQAC can also be made negative. So, if I want to have, let us say, braking operation, I would like to have a negative torque. So, instead of giving a response like this, what I will do here, I can also make this IQS negative. So, if the IQS is made negative, the torque will also follow IQS, that will also be negative. So, it means an induction machine, which is a fairly complex machine having multiple variables, and it is also a nonlinear machine. I can control it just like a separately excited DC machine by keeping the flux constant. However, in some situations, especially when the machine goes beyond the base speed, the flux has to be decreased. There is some genuine need for the decrease of the flux. Now, we would like to evaluate the response of the machine when the torque is varied, the flux is varied, torque is kept, the torque is controlled by controlling the flux. If we change the flux, how is the torque response look like? So, we can now see the response of the vector control drive with variable rotor flux. So, we will first derive a few equations, and the equations can be explained by means of a block diagram, and we will see if we try to vary flux, whether the torque response is instantaneous or it is delayed. So, let us first write down the equations for flux variation. So, what we will see here is the following, that as usual we know that psi qr is equal to 0, but psi dr is not constant, and we can write down the rotor equations. We can say that VDR, the rotor d axis equation, equal to 0, that is equal to RR IDR plus P psi dr minus of omega SL psi QR. But we know that in case of a vector control drive, there is no q axis rotor flux. So, we can make this equal to 0, this component does not exist, and if this component does not exist, we can further simplify this equation. 0 is equal to RR IDR psi dr is not constant. So, if psi dr is not constant, unlike the previous case when psi dr is constant, we cannot make P psi dr equal to 0. We must know that P is equal to the derivative operator d by dt. So, P psi dr is not equal to 0, and we would like to, what we would like to do here, we would like to eliminate IDR. IDR is not easily measurable. IDR is the rotor current in the d axis. The rotors are inaccessible, so we cannot measure the rotor current. So, what we will do, we will try to replace IDR by the stator currents and the flux linkage. So, we can say here that the expression for psi dr is equal to LR IDR plus LM IDS, and we can say here that IDR equal to psi dr minus of LM IDS by LR. So, what we will do here, we will replace this IDR in this equation and simplify what is the expression for this equation is giving us IDR. So, what we will do in this case is the following, that we will be replacing the expression for IDR in this equation and simplify and get the expression for the flux linkage, that is psi dr. So, if we do that, we will get the following equation. This equation of the rotor can be rewritten in the following way: 0 is equal to RR by LR into psi dr E minus LM into IDSE plus P psi dRe. Again, we can further simplify this. 0 is equal to 1 by tau r into psi dRe minus Lm into IDSE plus P psi dRe, or this can be rewritten as 1 by tau r plus P into psi dr minus Lm by tau r into IDSE, or we can say here that IDSE is equal to 1 by Lm into 1 plus tau r P into psi dRe, or psi dRe is given as Lm by 1 plus tau r P into IDS. So, this is an interesting equation in the sense that if we try to change the flux component of current, that is IDSE, if we want to change this IDSE, we will see that the flux is not proportional to IDSE. It is basically a differential equation, and when we try to change IDSE, the flux will be delayed, and the time constant here is tau r. And that is the reason if you change IDSE, because we have two ways to control the torque. Either we can control IQSE or we can control IDSE. And how do we control these currents? These currents can be controlled through inverter. We know that the inverter is ultimately injecting current onto the windings of the induction machines, and if we can control the inverter suitably, we can control either IQSE or IDSE or both. So, if we do the proper inverter control and we control IDSE, keeping IQSE constant, the flux will be delayed, and when the flux is delayed, the torque is also automatically delayed. So, we can explain this by means of a block diagram. The block diagram will look like this: control block diagram. So, we will have the similar structure here, and we can control either IDSE or IQSE, and if we control IDSE, the flux is not controlled proportionately. We have a delay term here, 1 plus tau r P, and this is our flux psi dRe. And then we have a multiplier block here. Then afterwards, what we have here is a gain block, is 3 by 2 P by 2 Lm by Lr. Then we have the torque. So, we see that if we change IQSE, the change will be instantaneous, because the IQSE goes directly to contribute the torque. Now, if we change IDSE, the torque change will not be instantaneous. It is basically going through a delay block. So, if we want to increase the flux by increasing IQSE, or if we want to reduce the torque by reducing IDSE, the torque will change definitely, but the torque change will be accompanied by a delay. Now, this can be explained by means of control response. So, if we see the control response, we will see that the torque change will be accompanied by a delay. So, we can see the response with variable IDSE, or in bracket we can say variable flux. So, we can see the various control response here. This is origin, and the x axis is the time axis. And what we will see here is that we keep IQAC constant. The torque component of current is IQAC, that is kept constant. So, this remains constant here, and IDAC is given a step change. This is our y axis, and IDAC is given a step change. And moment this IDAC is given a step change, the flux response, if you see the response of the flux was initially here, it will be delayed. The flux response, there is a first order delay, and the delay is due to the fact that it is 1 by 1 plus tau r p. This tau r is the time constant by which the flux will be delayed. So, if we change IDAC, the flux component, that is psi dr, does not change instantaneously, that is delayed, and due to the delay in flux, the torque will also be delayed. So, if we see the torque in this case, this is the torque. Initially the torque was some value, and the torque will also be delayed. This is Te, and this is psi dre. So, this response, the control response that we have shown here, takes into account the variation of IDAC. We have applied a step change in IDAC, and we thought the torque will also change, but the torque change is accompanied by a delay, and hence it is always advisable for having fast response. It is advisable to keep the flux constant. So, to keep IDS constant and change IQS to control the torque, and if we change IDS, the flux will change with a delay, which will also delay the torque response, as seen from the following control response. So, this is what we have here, and what is the solution? Say for example, sometimes we would like to change the flux, sometimes we would like to decrease the flux depending upon the requirement. So, if we want to change the flux, we have to have a compensated or a compensator to compensate for this delay. So, if we can have a compensator, we can compensate for the delay in the torque response, and that is called a compensated flux response. So, what you have here is the following, that this is the region of the delay. Now, if you see that this block diagram in this case, what we have here is Lm by 1 plus tau r, and this is within the machine. So, this dashed enclosure is within the machine. We cannot do anything inside the machine. The machine is running, and it is the behavior of the machine that if you change the flux component of current, the torque will be delayed. So, what we do here, we can add something here, of course. We can add something before this, that the delay can be cancelled, and we will see how we do that. So, compensator to cancel the delay. So, in this case what we have, we can draw the earlier block diagram. We have here Lm by 1 plus tau r p. The flux response is delayed here, it is psi dr. We have no control over that inside the machine. So, these are multiplied, and then what we have here is 3 by 2 p by 2 Lm by Lr. This is the torque. this is IQS, this one is IDS, and this is IQS, and this dash box is inside the machine. Okay, this is the machine, induction machine. And what we do here, we can add a compensator. Now, how do you add a compensator? We can add a compensator in the following fashion. So, we can add a compensator here, and the compensator will have 1 plus tau r p by ln, and this is my psi dr E reference. So, this shown in the blue diagram or blue color is the compensator, and the compensator is so designed that it can cancel the delay generated by the machine. We have a pole here inside the machine, and we have a 0 in the compensator. So, there is a pole 0 cancellation. When you have a pole 0 cancellation here, the delay is removed. And if we see the response in this case, when we apply step change in the flux, the torque also changes instantaneously proportional to whatever the change we have applied in the flux. So, if we see the response here, in this case, this is our time axis, and let us say we have given a step change like this in this psi dr star, and the torque component of the current is constant. This is IQS star. Although we have applied a step change in the flux in this case, there is no delay. Why there is no delay? The delay is not there because the flux component varies like this. Due to the derivative term in the controller, the flux component will change like this, and that is how this delay is cancelled. This is my torque, and the torque will also change proportionately. So, we can see that this is the torque response, and this one is IDS E, and the lower one is the torque. So, we see that when we have a compensator, the compensator has a derivative term, and the derivative term is responsible to give a spike in the flux component of current, and that current kick is able to compensate for the delay in the flux, and the torque varies instantaneously as we vary the flux. So, this is an example how we can have a controller to compensate for the delay in the flux. We have already seen the response of a vector control drive, and the response of a vector control drive with constant rotor flux, and the response of a vector control drive with variable rotor flux, and the response of a vector control drive when we have a compensator to compensate for the delay in the flux response. Now, after this we will try to see that how to estimate the rotor flux. Unless we estimate the rotor flux, we cannot go for the compensation. We cannot go for vector control. So, we have to estimate the rotor flux, and as we know that the key to this is the following, that we have to estimate this angle theta e, which is tan inverse of psi q r by psi d r. So, we have to find out this angle, and this is the angle of the rotor flux vector with respect to the phase A axis. So, if we have phase A axis here, these are the 3 phases of the machine, and we have the rotor. The rotor flux is rotating synchronously at a speed of omega e. This is the vector, that is psi r, and this angle we have to estimate, theta e. And if we estimate this angle, or if we can find out this angle can help us to transform the current components IDAC and IQAC into the actual stationary current ABC currents IA, IB, IC. So, the hypothetical currents IDS, IQS, we have, this is our D axis and this is the Q axis, and correspondingly we have IDS and IQS. We have to use this angle theta e to transform the currents IDS and IQS into IA, IB, IC. So, we have to find out this angle of the flux vector, that is theta e, and hence we have to go for what is called rotor flux estimation. The rotor flux is not directly available, it is inside the rotor. The flux linking the rotor is called the rotor flux, and you know that people have tried to find out the air gap flux, the stator flux, but the rotor flux is difficult to measure. Putting a sensor inside the rotor is not very convenient. We cannot just put a hole or make a hole, put a sensor in the rotor, because the rotor is rotating, we cannot have a sensor inside the rotor. So, we have to somehow estimate the rotor flux from the terminal variables. The terminal variables are voltages and currents. If we can estimate the rotor flux, it will solve our purpose, in the sense that we can find out the angle of the rotor flux vector to effect the transformation from IDAC, IDS, IQS to IA, IB, IC. So, in this case what we have, we can have 2 approaches. One is called a voltage based estimation, and in the voltage based estimation what we do, we primarily rely on the voltages of the machine to estimate the rotor flux. So, we take the voltages, we integrate the voltage to find out the rotor flux. So, this is one way, and the other way is a current based estimation. In a current based estimation, we do not integrate the voltage, we take the currents and take the help of the currents to find out the rotor flux vector, and both the approaches have their own merits and demerits. The voltage based model is suitable for higher speed, and the current based model can be applied throughout the speed range without any difficulty. But the voltage based estimator is little easier to implement, because this requires less signal processing, but the current based method requires more signal processing and hence is computationally intensive. So, this relies on the voltage, primarily integration of terminal voltages, and this is more suitable for higher speed. Typically greater than 10% of the base speed, and the current based estimation is computationally intensive and suitable for throughout the speed range. Now, first we will discuss how to do the estimation using voltage based technique. Right now we will be discussing the voltage based technique to estimate the flux. So, we have the terminal variables available to us. So, we have the voltage based flux estimator model. Now, we can find out what is IDS. IDS is 2/3 IA minus 1/3 IB minus of 1/3 IC, and that is equal to IA. So, this IDS is the current in the DQ stationary reference frame. So, we can say this is the stationary reference frame. So, IDS is the stationary reference frame current. And similarly, we can find out IQS in the stationary reference frame. So, we can say that IQS is equal to 1 by root 3 into IB minus 1 by root 3 into IC, that is equal to 1 by root 3 into IB minus IC, and that is equal to 1 by root 3 into IA plus 2 IB, because we know that IA plus IB plus IC is equal to 0. We can eliminate IC. IC is equal to minus of IB plus IA. So, if we substitute for IC, we can see that it is IA plus 2 IB 1 by root 3. And what we do here, we have to only measure IA and IB of the machine. So, the machine is a 3-phase machine. So, we have a 3-phase machine here. These are the 3 different phases. This is the induction motor, and we have here phase A, phase B and phase C. And since we have a 3-wire system, we can always say that IA plus IB plus IC equal to 0. So, in that case, this is the IA and this is IB and this is IC. We do not have any neutral connection here. We have just a 3-phase system, a 3-phase 3-wire system. So, we can say IA plus IB plus IC is equal to 0, and applying that we can find out what is this IDS and what is the IQS. So, if we measure, if we have a current sensor, so we can have a current sensor here, and this current sensor will be giving us IA, and this current sensor will be giving us IB. So, we have IA and IB available to us. From IA and IB, we can find out what is IDS and IQS. And in a similar fashion, we can find out what is VDS and VQS. VDS is equal to, in the same way, we can say here it is 2 by 3 into VA minus half VB minus half Vc. This is actually based on the stationary reference frame transformation, which we have already done a few lectures back. So, we know that in case of a stationary reference frame, theta e is equal to 0. So, if you substitute theta equal to 0 here, the angle of the reference frame is equal to 0, we can get back this as 2 by 3 into VA minus of half of VB minus of half of Vc, and this we can simplify, and that is equal to 2 by 3 VA minus 1/3 VB minus 1/3 Vc. So, I can take 1 by 3 out. So, I will say here it is VA minus of VB plus VA minus of Vc, that is equal to 1/3 of VAB plus VAC. So, what is VAB? VAB is the line voltage between A and B. So, if I have a voltage sensor, if I can have a voltage sensor here, this is a voltage sensor, this voltage sensor will be measuring VAB. And if I have a voltage sensor between A and C, this will be measuring VAC. So, I can have a two current sensors and I can have two voltage sensors to find out IDS IQS and VDS VQS. Please remember that these IDS and IQS, VDS and VQS are the variables in the stationary reference frame. In other words, the reference frame in which we are calculating these variables for finding out the flux linkages are not rotating at the stationary reference frame. It means if I have my reference frame, the reference frame has a D axis and the reference frame has a Q axis, and the D and Q axis are stationary in the space. They are not rotating, they are stationary in the space, and correspondingly this will have VDS, IDS, this will have VQS and IQS. That is what we are computing from the terminal variables. They are the voltages and the currents. And from this we can find out the flux linkages. Now, how do you find out the flux linkage? The easiest flux linkage is the stator flux linkage. So, we can say that psi ds equal to integration of VDS minus IDS RS, alright. So, this is what we can say very directly. So, we can evaluate the stator flux linkage by integrating the voltage VDS minus IDS RS, integration of that will give me psi ds. And in a similar way I can find out psi QS is the integration of VQS minus IQS RS. So, the integration of the induced EMF, the induced EMF behind the stator resistance, the integration of that will be giving me the stator flux linkages, psi ds and psi QS. But I do not need the stator flux, what I need is the rotor flux, because our vector control aims at the orientation with respect to the rotor flux vector. So, I have to find out the information about the rotor flux. So, we will go stage by stage. Now, we have been able to evaluate the stator flux linkage. So, from that we can evaluate the air gap flux. As we have already seen that in case of a machine, if we only represent the inductance part, this is the stator leakage inductance, this is the rotor leakage inductance, and this one is the magnetizing inductance of our induction machine per phase circuit, and this one is the stator flux. We can call this to be psi s, and this flux linking the magnetizing inductance is called the magnetizing flux or the air gap flux, and the flux linking the rotor is the rotor flux, that is psi r. So, what we have done here, we have been able to find out the stator flux linkage, that is psi ds and psi qs. From that we can evaluate what is the air gap flux linkage or the magnetizing flux linkage, psi dm and psi qm. So, we know that psi dm is equal to psi qs minus psi dm is equal to psi ds minus the stator leakage. So, this is Ls IDS, this is the stator current, this is the rotor current, and similarly we can evaluate psi qm is equal to psi qs minus Ls into IQS, and we have to go again further. What we need here is the rotor flux. So, if we want to find out what is psi dr, psi dr is psi dm plus the rotor leakage flux Lr into IDR. Similarly, we can have also in the q axis psi qr is equal to psi qm plus Lr into IQR. So, we are proceeding stage by stage, step by step. Ultimately what we need we need psi dr and psi qr, and if we need psi dr and psi qr, we can find out the rotor flux vector angle. So, to evaluate psi dr and psi qr, what we need here is this: the rotor currents are not available to us. We can always measure the stator currents. We can find out easily IDS and IQS by measurement, but can we find out what is IDR and IQR? IDR and IQR are not available to us. They are inside the rotor, and sometimes the rotor is a cage rotor, a squirrel cage rotor. If the rotor is a cage rotor, we cannot have any idea about the rotor current. So, we have to express the rotor current in terms of other variables which are measurable. This IDR is in the following fashion. We know that psi dm is equal to Lm into IDS plus Lm into IDR. So, what we do here, we calculate, we evaluate what is IDR. IDR is psi dm minus Lm IDS by Lm. So, we can evaluate what is IDR, and then we can similarly we can evaluate what is IQR. IQR is equal to psi qm minus Lm IQS by Lm. So, we can find out what is IDR and IQR in terms of IDS and IQS which are measurable, and then we can substitute this back here to find out what are the stator fluxes, rotor fluxes. So, this is the way in which we can evaluate the rotor fluxes from the terminal variables. Now, this actually is very appropriate when the speed is high, and the main bottleneck of this method is that whenever we have low speed operation, when the speed is very low, it is difficult to integrate the voltage to find out the flux linkage. Now, this is the difficulty in the measurement. As we are going step by step, we are evaluating the air gap flux or the magnetizing flux from the stator flux. So, the stator fluxes are evaluated by the integration of the voltages VDS and VQS, and whenever we have an integrator, we have a practical integrator, the integrator will be having some offset, and offset is usually very small when the voltage is significant. Voltage is large compared to the offset. Say for example, offset can be in the order of few millivolts, but if the voltage is very large in the order of few tens of volts or hundreds of volts, this offset can be ignored. But as we are talking about low speed operation, the speed is close to 0, the voltages will also be very, very small, because we understand that when the speed reduces, voltage also reduces with the speed. So, at low speed operation, the difficulty of this method is the following: at low speed operation, the integration of voltage to evaluate flux linkage becomes erroneous. So, at low speed, the voltage becomes small and the voltage is comparable to the offset of the integrator, and then the integrator becomes erroneous, and if the integration is not correct, the flux linkage will be also incorrect, and hence we can't get a good estimate of the flux at low speed region. And due to this, this method is applicable for a speed higher than 10% of the base speed. Hence, voltage based estimation is preferred only for speed greater than 10% of the base speed. So, this is basically the limitation of the voltage based method. Now, to overcome this limitation, we have another method called current based estimation technique. So, we will discuss current based estimation after deriving the equation for the same. So, we will be discussing about the current based estimation technique. So, in this case what we will be doing here, we will be taking the rotor equations, and from the rotor equation we will be deriving the current based estimator. So, we have the equations as follows. We can say that the rotor equations in stationary reference frame can be given as follows. Say for example, we can say that psi dr equal to RR IDR plus P psi dr plus omega r psi qr. And similarly, we can write down in the q axis, that is equal to 0, VQR is equal to RR IQR plus P psi qr minus omega r psi dr, that is equal to 0. So, these are the currents in the stationary reference frame, the rotor equation in the stationary reference frame, and this will be useful for deriving current based estimation technique. Now, we will see how we do that. Now, if we simplify this equation, we will have the following equation. D by dt of psi dr this is equation number 1, we can say, and similarly we can have d by dt of psi qr plus RR IQR minus omega r psi dr, that is equal to 0. This is equation number 2. So, what we do here, we add in this case RR into Lm by Lr into IDS to the left hand side and right hand side of equation 1. So, if we add this quantity in the left hand side and the right hand side of equation 1, we get the following equation. So, from this equation we can get back a new equation by adding this particular term, and this equation is the following. So, we have d by dt of psi dr plus RR IDR plus RR Lm by Lr into IDS plus omega r psi qr equal to 0. And we can further simplify this. What we will do here, we will take this RR by Lr common. So, we have here Lr into IDR plus Lm into IDS plus omega r psi qr, that is equal to 0. Or we can just write down this P is the derivative operator psi dr plus RR by Lr is 1 by tau r, and this quantity within the parenthesis Lr into IDR plus Lm into IDS, that is psi dr plus omega r into psi qr, that is equal to 0. So, this equation can be called equation number 3. This is the equation in the d axis. So, from this we can find out the information about the rotor flux in the d axis. So we can just rewrite this equation once again. P psi dr plus 1 by tau r psi dr plus omega r into psi q r into psi q r is equal to, there is a right hand side term also here, and the right hand side term here is Lm by tau r into IDS. So this is in the right hand side, Lm by tau r into IDS, Lm by tau r into IDS. That's equal to Lm by tau r into IDS. So this is the equation number 3 that we have already derived. And after we simplify this equation, we can get this P psi dr is equal to Lm by tau r into IDS minus 1 by tau r into psi dr minus omega r into psi q r. This is the same equation. So this equation is the equation in the d axis. Similarly, we can have the equation in the q axis and simplify, and we will have a similar equation in the q axis as well. So in the q axis, we have P psi q r, that is equal to Lm by tau r into IQS minus 1 by tau r into psi q r. This speed induced EMF will have a different sign. So we have plus omega r into psi dr. This is the equation number 4. So from equation number 3 and 4, we can evaluate the rotor flux linkages. So this can be explained by means of a block diagram. If we draw a block diagram, it will be easy to understand how we can estimate the rotor flux from these two equations. So we have a summary here, and here what we have in this case is Lm by tau r, and this one is IDS coming from outside. Similarly, in the q axis we have again another summer. This is Lm by tau r. So this is IQS. So this is plus, and then what we obtain here out of this is P psi dr, and we use an integrator here. And what we obtain here is psi dr. Similarly, out of this we obtain P psi q r. We use an integrator here, and then what we obtain here is psi q r. And we have to do some readjustment in this case. Here is a feedback loop. We have to feedback the flux linkage vector or the flux linkage 1 by tau r, that is obtained from this. So here is a negative sign. Similarly, we have a feedback mechanism here as well. One by tau r, and here we are feeding back 1 by tau r into psi q r, and here we have the speed. This is omega r as an input, and this is fed to this place after suitable multiplication. So in this case we see that we have a term called omega r into psi q r. This is my omega r, and this is the psi q r. So this is omega r into psi q r. Similarly, I have another multiplier here, this will go in this case, and this will be, this is minus, and this will be plus. So, this is coming from side ER, and this is the speed that is coming from here. So, this is again fed back to this particular block. So, this is the complete estimation. So, this is actually a current based estimation technique, and this does not integrate any voltage. Currents are always available. So, we can integrate the currents, and if we integrate the current, we can find out the flux linkage, psi dr and psi qr.